In this video, we will explain about the working of cache memories. The speed of the main memory is very low in comparison with the speed of modern processor. It is important to devise a scheme that reduces the time needed to access the necessary information. An efficient solution is to use a fast cache memory, which essentially makes the main memory appear to the processor to be faster than it really is. So this is a typical computer memory hierarchy, and we have this is our processor, then this is main memory, this is our storage, that is magnetic disk or secondary memory. Then comparing to the processor, the main memory is slow and the magnetic disk is slow comparing to main memory. Okay. Then to improve the performance or speed of memory access, we can introduce cache memory in between the processor and main memory. So this is our cache memory system. Here we have two levels of caches, primary cache L1 and secondary cache L2. Normally the primary cache will be inside the processor chip. So the cache memory, the speed of the cache memory is more as compared to the main memory, because this cache memory is made up of static RAM technology. So the speed is more comparing to the main memory, because main memory is made up of DRAM chips. Then the speed is increasing in this direction, that is magnetic disk is slow and register is having highest speed. Then the increasing cost per bit, the cost per bit is also increasing in this direction. The cache memory is costly comparing to the magnetic disk or main memory, and size is increasing in this direction. Magnetic disk has huge storage, then main memory, then cache, then L1 cache, like that. Register is having very small memory. And when a processor wants to access a particular memory, processor will first look into the primary cache. If that data is available in the primary cache or L1 cache, we will call that as a hit or L1 hit. Data is present within the primary cache, so the processor can read that data. And if the data is not available within the primary cache or L1 cache, then we will call that as a L1 miss or primary cache miss. Then we will look into the secondary cache. If that data is present within the secondary cache, and we will call that as a L2 hit. Then the data will be brought into L1 cache. From L1 cache, processor can read that. If the data is not present within the L2 cache also, then we have to look into main memory. If that data is present within the main memory, then the data will be first brought into secondary cache or L2 cache, then that is brought into L1 cache, then the browser can read that data. Okay. And if the data is not available within the main memory also, then we have to bring that data from secondary storage into main memory, then to secondary L2 cache, L1 cache, and processor. So the communication between main memory and secondary storage will be we are not discussing in this session. That you will study in operating system topic virtual memory. In that case, that will be implemented by using a mechanism called paging. Okay. Then that's about the working of the basic overview of the cache memory. The effectiveness of the cache mechanism is based on a property of computer programs called locality of reference. Analysis of programs shows that most of their execution time is spent on routines in which many instructions are executed repeatedly. These instructions may constitute a simple loop, nested loops, or few procedures that repeatedly call each other. First, we have to discuss about the there are two types of locality of reference: temporal locality and a spatial locality. Temporal locality of reference: a recently executed instruction is likely to be executed again very soon. The temporal aspect suggests that whenever an information item is first needed, this item should be brought into the cache where it will hopefully remain until it is needed again. Spatial locality of reference: instructions in close proximity to a recently executed instruction with respect to the instruction's address are likely to be executed soon. The spatial aspect suggests that instead of fetching just one item from the main memory to the cache, it is useful to fetch several items that reside at adjacent addresses as well. So let us consider a simplified diagram of this cache memory system. This is our processor, this is main memory, and we have a cache memory in between this processor and a main memory. We are just considering only one level of cache here for simplicity. So when a read request is received from the processor, the block of memory words containing the location specified are transferred into the cache. Subsequently, when the program references any of the locations in this block, the desired contents are read directly from the cache. So this is a typical cache memory and a main memory system. This is our cache memory and this is our main memory. And cache memory is divided into a number of equal sized blocks called cache block or cache line. Similarly, the main memory is also divided into a number of equal sized blocks called main memory blocks. The size of the main memory block and a cache block will be the same, but the number of blocks will be more in the case of main memory, and that is less in the case of cache memory because the cache memory size is less. Then initially the cache memory will be empty. That is, when we turn on the cache memory, the cache memory it is made up of static RAM cells, so that will enter into some state. The cells will enter into some state and into some stable state, and these blocks will have some garbage value. So in that case, if there is no valid data, then there is an associated bit called valid bit that will be set into 0. So corresponding to each block, we will have a tag field and a V bit or valid bit. This valid bit is used to indicate that whether this block is a valid one or not, whether it is a garbage value or a valid block. This tag is used for another purpose that will be discussed later. So corresponding to each block, we will have a tag field and a valid bit field. So okay. Then initially this entire cache will be empty, or all the blocks are invalid. The V bits will be all set to 0. Then assume that the processor wants to read a data from the block, a word. Processor wants to read a word present within the memory block 129. Okay, first we will assume that our cache memory in this example, this cache memory is divided into 128 blocks, block 0, block 1 up to 127. There are 128 blocks, and each block is having a size of 16 words. Then similarly, main memory is divided into 4096 blocks, and each block is having the same size, that is 16 words. Then if the processor wants to read a word present within this block 129, memory block 129, then initially the processor will check into the cache memory into corresponding location. So initially that block will not be here, so a cache miss will occur. Then the block 129 will be loaded into a particular location, a particular block within the cache memory. Assume that it is loaded into block 1. So block 129 is it is loaded into block 1. then the corresponding valid bit will be set to 1. That is, it contains a valid block, valid memory block. And the tag will also be set accordingly. That will be discussed later. Then, okay, the data required, the requested word will be delivered to the processor. If the processor again requests a word that is present within the same block 129, then it will first check into cache memory. Okay, the processor identifies that, okay, that the block corresponding to that word is present within the cache memory, so a cache hit will occur and the data will be delivered from the cache memory. So there is no need to go to the main memory. Okay. So usually the cache memory can store a reasonable number of blocks at any given time, but this number is small compared to the total number of blocks in the main memory. The correspondence between main memory blocks and those in the cache is specified by a mapping function. That's how the main memory blocks will be placed into the cache memory blocks. That is, which block can be placed into which cache memory blocks. When the cache is full and the memory word reference is not in the cache, then the cache control hardware must decide which block should be removed to create a space for the new block for that contains reference word. That is, cache is currently full and the requested word, the block containing the requested word is not present within the cache. Then a cache miss will occur. Then we have to bring the block containing the word from the main memory to cache. So in that case, we must make a space within the cache memory. For that purpose, we have to evict or remove one block from the cache memory. Which block to be removed? How to decide which block to be removed? We have to use some strategy. So that we'll call as a cache replacement algorithm. The collection of rules for making this decision constitute the cache replacement algorithm. Next, we have to discuss the terminology cache hit. If the addressed word is in the cache, it is called a read or write hit. On read hit, the data is obtained from the cache. On write hit, the cache has a replica of the contents of the main memory. So in the case of a write, the content of the block will change, but the block within the cache and the main memory must be consistent. So how to make that consistent? For that purpose, we will use mainly through protocols, write through protocol and write back protocol. In the case of write through protocol, the contents of the cache and main memory may be updated simultaneously. In the case of write back protocol, update the contents of the cache first, then mark it as updated by setting a bit known as dirty bit or modified bit. And the content will not be written at that time itself, but the content will be updated or returned back to the main memory block, corresponding main memory block, only when this block is replaced from the cache memory by another memory block. That's about the write back protocol, and these two protocols have the corresponding advantages and disadvantages. Cache miss. If the addressed word is not in the cache, it is called a read or write miss. On a read miss, the block of words containing the requested word is copied from the main memory into the cache. After the block is transferred, the desired word is forwarded to the processor. And the desired word may also be forwarded to the processor as soon as it is transferred without waiting for the entire block to be transferred. This is called a load through or early restart. And cache on a write miss. If write through protocol is used, then the contents of the main memory are updated directly. That is, first the content of the main memory block is updated, and then that block is brought into the or loaded into the cache memory. If a write back protocol is used, the block containing the addressed word is first brought into the cache, and the desired word is overwritten with the new information, and the change will not be updated at this time itself. The change will be updated only whenever this block is evicted from the cache or replaced from the cache memory by another block. Mapping functions. The correspondence between main memory blocks and those in the cache is specified by a mapping function, and these are the different cache mapping functions. One is direct mapping, associative mapping, and set associative mapping. We will discuss each of these mapping techniques in detail in the next videos. Okay.